So I guess some of the people weren't here last week, James. So just tell us again, how long were you have you been working on CCS now, do you think?
2006, so 15 years.
15. Very good.
The first project was that year. I'm just reveling in the fact that I'm that old now.
The peak of your life. Could be. I mean, it could all be happening now. What was your first degree? What did you by sort of training?
Chemical engineering.
And do you think you've carried on using chemical engineering, or would you say you've got into other areas?
I've gone into other areas as well. I think the way chemical engineering is taught now is slightly more dynamic, but along the way, I've had to delve into policy and how to talk, do engagement. I've become fascinated by social engineering and the social side and social impact of energy transition. And for a good part, I've had to be self-taught on how to be a pipeline engineer, which is something my chemical engineering brethren will probably look down on with a great deal of dismay. But you can't, if you're going to be working on infrastructure projects and network projects, you at least have to be able to keep up with the proper pipeline engineers and understand the raw basics. So it's been a never-ending challenge to keep your skills fresh and relevant and learn.
You sort of raise a question then. Do you think there's anything the UKCCSRC could do on that, or do you think it's a little bit too specialised?
Well, in terms of teaching?
Yeah, well, I mean, I suppose there's teaching, and I suppose there's also what you're describing as maybe a bit more awareness. So you might not feel competent to have to teach people, but you might feel competent, or at least useful, to make them aware of some of the issues. So a bit more than, not superficial, but
I think so. The short answer is yes. I think there might be something that we can do there, given the people that we have involved in the UKCCRC that can talk about policy and social engagement and all of those things. I think there's a lot there that we can distill down to the ECRs and everyone else. And I've seen some of the success that's come out of Scottish Centre, for example, when they did their back in the day when they did the CCS geology 2-day course, which I went on because I needed to understand how things react when I try and push carbon dioxide into them. That was a good example of it rolling out. The master's course at Edinburgh was a nascent idea of everybody's. I think just it needed to be done, and the change that it went from a very geology-based subject to include more engineering was a direct impact of effectively Hannah talking to all the industry people and then changing the course to do that, and those kind of things. And I think UKCCSRC is in a perfect place to encourage industrialists to do what I do and pitch up at least once a year and educate people from an industry's perspective on the master's courses and things like that, because this was only the second year in 12 years I've missed doing the master's course at Edinburgh, because I normally go up and talk to them about pipelines and infrastructure for a good 3 hours once a year, but this year I couldn't because I was on garden leave.
Okay. Well, that's something to think about. Anyway, we should get on, but I think that, there's an awful lot of people coming into the industry now, and people can't get aware of everything instantly.
No, they can't.
It might be quite useful. Okay, all right. Well, thanks very much. I'm sure we'll learn a lot over the next 50-odd minutes. So, floor's yours, James, and thanks again for coming to talk with us.
Thanks. I will just try and figure out how to share my screen. We'll share that one. Oh, and go bang. So do you see the full presentation?
Yeah, that looks great.
Right, cool. And I'm very pleased that I've managed to, I remembered to change the title about 3 minutes before I came online. So good afternoon, everyone. My name's James Watt. I'm going to talk to you this afternoon about CCUS Infrastructure and Clusters, following the pipeline lecture, the pipeline one last week. It says hydrogen consultant down at the bottom. That's my role within WSP, is actually to look now at hydrogen infrastructure. But I have a background, as you just heard John ask me, in CCS infrastructure going back to 2006. I've been with WSP 3 months, but prior to that, I was with the engineering company Wood, which was previously known as AMEC and AMEC Foster Wheeler. And I've done while I was there, executed a large number of CCS cluster studies, mostly in the UK. And from the very first one in 2006, which was perversely, I think, Mersey and Dee Basin, which is morphed into HyNet these days. And I've worked on clusters in for Scotland, Teesside, Humber, Yorkshire, and another few places. That's just me because I realised I didn't do it last week. But yeah, as I said, 15 years, the cluster studies. I think last time I did a count of how many cluster studies and pipeline jobs I've been involved in for CO2. It's getting close to a couple of dozen now. My major projects, and most of this work was conducted at Wood because I was there for 20 years. But my experience also includes the major feed projects for the Longanet CCS project, which we designed the pipeline and compressor station for. I was part of the owner's engineer team on the Masdar for feed and EPC CO2 project. I was involved in Don Valley, and I was the technical lead for the Teesside collective work back in 2015 and a few other things. And I've been involved in hydrogen, so I was involved in the H21 Lead Citygate, which had a CCS element to it as well, and the SGM H100. What is CCS infrastructure? And it's hard to sort of quantify because people use terms interchangeably, but this is how we look at it in terms of hardware, or how I look at it in terms of hardware. The infrastructure is the bit that knits everything together. You have emitters with capture plants. You have to get that carbon dioxide to the store. And the infrastructure is the pipelines, the compressor stations, the pumps, the shipping for transport options, the offshore platforms, whether it's templates or buoy offloading, or platforms with wellheads, or EOR, if we want to go into that. It's about providing the CO2 to where it needs to go, and then effectively getting it down the hole. In terms of where infrastructure or pipeline design finishes, it tends to finish at the wellhead valve, whether subsea or above sea level on platforms. That's where it ends. But that's roughly what I mean by infrastructure. Included in that is, how do all of those bits communicate? How does that network, how does that infrastructure all operate? How does it deal with the dynamics? How does it deal with the individual emitters or different stores, or those variabilities? So it's not just the hardware, it's not just the pipes, it's not just the compressors, it's about how that all interacts. How do you do the metering, the commercials, the understanding of risk, who owns the CO2, who's liable for the CO2 going forward. So it's actually quite a broad subject. And many years ago, I used to wind a particular professor up by saying it wasn't CCS, it was carbon capture, utilization, transport, storage, and it doesn't, the transport and infrastructure, or transport bit and the infrastructure bit tends to be missing. And early projects looked at the cross-chain impact of the designs and control systems. So that's what we mean by infrastructure, kind of represented in a very simple diagram. What do we mean by full chain? And I say this because I will at some point inevitably talk about chain, the full chain. So the full chain is from the emitter, not just the capture plant, but the emitter, the actual home plant that the capture plant's attached to. through to the storage and subsea completions, and you can add the measuring, monitoring, and verification on the end of that, because it plays a role once it's designed and operating. It's important to realise, and it's something I covered last week, this is an example of one, and it's important to realise the impact the individual bits have on a chain. So this is originally from a coal-fired power station, originally drawn for the CASM project back in the day, back in 2007, 2008, that we did with a group of universities. And these are the principal design elements, or the more critical principal design elements in each block that impact the blocks around it. So, for example, you can see in dehydration, we have water as a key composition element that impacts the compressor going forward, but also impacts the design of the stripper and the capture plant to minimize the amount of water you've got through. There's a lot of steps, there's a lot of blocks. The infrastructure is typically the pipeliney bit in the middle in terms of hardware, the compression pipeline, boosting pipeline, if you have boosting. With infrastructure and clusters, that's great. You'll probably have those 4 blocks, the compression and pipeline block, as the main trunk line that goes off to the store, but you might have 10, 5, 15, 30, 300 different emitters with all different design parameters that all push onto that infrastructure and how that infrastructure is designed. You might have 3 or 4 stores with different conditions that have to be balanced, and the flows have to be managed, all push back onto the infrastructure. So that link in the chain of infrastructure is really important. So a couple of other things. So A to B, source to sand, source to store, whatever you want to call it. This is the traditional where we started back in 2006, I think, with the likes of DF1 and Longannet and Kings North and the early competitions that the UK government launched, which didn't include clusters. This is their solution. You have an emitter that goes through an infrastructure pipeline to a store or platform, whatever. The rate of emission competes with the rate of injection. The quality of the gas and the flow rate injected is the quality of gas, the flow rate emitted effectively. And there's some pushback from the downhole conditions. So the systems approach each other from each end. The emitter is pushing in a certain way, and the storage will push back in a certain way. And you just have to marry up those individual components for that single project. That becomes easier when you look at the next evolution. It's still source to sand. It's still a single emitter to a platform, to multiple wellheads. Multiple wellheads give you more flexibility. That means you can expand storage sites. You have less pushback onto the network. So we end up saying giving more degrees of freedom in the storage end for the source to sands helps. That's an improved infrastructure over the basic A to B solution. Where networks become more complicated is when you start adding stuff at the front end and adding more emitters. With new infrastructure, and it is mostly new infrastructure, although we'd look to reuse some. The emitter drives the process. Storage and transport push back. So storage defines what composition is acceptable to the store. That does not necessarily meet with what the emitter wants to do. So the emitters will want to capture the carbon dioxide, and they won't want to clean up the gas any more than they have to. But we've kind of forgotten, and in early projects, there wasn't sort of research projects. It was a case of what the emitter gives you goes down the hole. The stores push back. There are things that you don't want to put down the wellheads for various reasons. So there is a design parameter based on the injection rate, the injection pressure and temperature requirements, and the composition that the store defines, and then pushes back onto the infrastructure and back onto the emitter. So the infrastructure can absorb or clean and absorb some of that variation, and could in fact clean it if that's what was needed, or remove some of those composition issues. But it has to meet that those injection rates and injection pressures and temperatures. The emitter in turn has an emission rate and a composition which also has to be accommodated, but there has to be some give. And what we tend to find in with the compromise between the emitter and the store is actually the composition. That there'll be an entry specification that is good for transport and good for the store, and the emitter will have to meet that criteria. That also means that there's some incredibly complex dynamic situations going on, in that you have two ends of a network, and of an infrastructure that are in effect in design terms pushing against each other in a little way. What we do know about network infrastructure is that A to B solutions are expensive. The reason for that is because time and time again, we've seen projects say we need X pipeline, X store, a platform of a certain size and certain shape. Those are very expensive bits of kit, bits of decisions that actually that wellhead or platform that you're using for your storage could accommodate a lot more. So adding more carbon dioxide into that infrastructure gives you a marginal increase potentially in pipe size, which is will give you only a marginal increase in cost. But the platform could accommodate more because they're adding wellheads. So as you utilize the equipment you're putting in with more carbon dioxide, you tend to find the prices drop over time. There's issues with emitter sizes and types, and they do vary in networks and infrastructures, network infrastructure. So if you have multiple users, they are not going to be the same size and shape. They are not going to be as capable of each other as responding flexibly, or they will have different compositions that need to be managed. There's always a question of whether you need more than one store on a common network, because if there is a fault that develops with the single store that you have, shouldn't you have another one? Which is why we go to multiple wellheads. As I said, the dynamics are relatively complex. More critically though, networks reduce the number of pipelines, and there's a number of reasons why that's a good thing. Cost is one of them, but predominantly the one we look at more and more is planning and getting permitted pipelines, particularly in what is actually a relatively crowded country. Getting the number of pipelines down to a reasonable number helps you not only win the public battle for getting infrastructure put in place, but also means that there's more space in the future for additional pipelines to come in if necessary. And time again, study after study after study has shown networks to be cheaper. Not for everybody, and we'll talk about that more a little bit later, but every study seems to show that networks are cheaper. So there are key factors, and we'll try and touch on them as we go. The first one is commercial. Who owns the risk and the CO2? Who pays what to whom? And the risks involved with the transport and the ownership of the carbon dioxide. Where does the CO2 go? So the route, how does it manage to get where it needs to go? With where is the store? Who owns the store? Those kind of things. Scenario planning. Networks are not just going to get built overnight. They are going to develop over time. The anchor project, the first project that goes, will be the only bit on the network day one. You will not have a lot of capital investment hinging in multiple emitters on one system working. They will naturally just tend to delay to make sure that the system is working. You have entry spec and access requirements. The owner of the network will have to define what people can put into the network and where they can put it in. Dynamics, again, that little word. Comparisons to the source and sink models, there's some of those that we'll talk about just to illustrate the costs. What can we reuse? And then how do you reach everybody? And that's one of the more nebulous problems that we face with clusters, in that clusters and network infrastructure can't actually economically reach everybody that needs a CCS solution via a pipeline or a ship. So you might be more into the more expensive realm of road transport or rail transport. So the dynamics, because I mentioned it a few times, and it's the hardest one to kind of explain. We look at the dynamics of infrastructure in the knowledge that there is carbon dioxide infrastructure in the world, particularly for EOR, and the top set of boxes on the flowchart recognize that. You have a CO2 source, you have a compression system, a pipeline, more compression and pumping goes in the wellhead, it enters the reservoir, enhances the recovery of the oil, you get more oil out going into refining. It is, like our gas networks, a demand-led system. You want to produce more oil, you add more carbon dioxide. However you figure the commercial arrangements for the provision of that carbon dioxide, if you don't want any more carbon dioxide, you just turn the tap off. You might end up paying for that carbon dioxide anyway, but it will get released and will become static in the pipeline. When we're looking at power and industrial emitters that are actually having to abate their emissions, so the driver here is the abatement of the carbon dioxide from the emitter, the dynamics change slightly in that the emitter has a drive. It wants to export its CO2 all the time. It has, for power particularly, has a variability that systems don't necessarily like very much. And there's potential correlations there with what we're looking at in hydrogen systems, and that there's a variability that pushes the network in a certain way. But the store will also have a feedback. It will also want you to operate in a certain way. It has the issues around permeability and pressure that mean your day-to-day changes or pushback from the wells might not be excessive or extreme. But over time, the store and the infrastructure has to develop and has a pushback. So you'll see more reservoir management being put into play, or more wellheads being added, or all of these kind of things. So the dynamics are pushing in both directions, which is not so prevalent in gas infrastructure and in the EOR type infrastructures that we've seen before. So you're pushing in both directions. Variability in those dynamics is also, and we've seen it before in projects, not wanted. We have seen over time stores telling us that they do not want a flexible or a varying load. They do not want to see large, sharp variations in the amount of flow coming to the well. They want to keep it consistent. They want to avoid shut-in. And understanding those variability drivers means that the emitter has to understand that it needs to respond, or you need some way of leveling off some of the more extreme emission profiles that we see. And the example here would be if you were looking at the hydrogen networks, which is what I do in my day job. If you allow a load following hydrogen production unit that's following the gas grid, the turn down on the gas grid is extreme and is actually only running at peak for a very short period at about 7 a.m. in the morning and 7 a.m. at 6 p.m. in the evening. The variability of that system is it would cause problems with CCS wells, because you can in the summer get prolonged periods during the day where you have no flow, so there'd be no output. That's a gross simplification of what the hydrogen network will look like, but it drives a dynamic problem that has to be managed and expected. So designing that new infrastructure and how do you do it is complicated. It's not easy. It requires a certain amount of leadership, and we've seen lots of people come up with cluster plans and ideas. The most successful ones are the ones that understand the marriage between policy, design, policy and the technical aspects, and guidance and the regulation. But the leadership that's needed is the drive to bring the emitters together, to engage, and to understand what the regulators or funders or financiers want, and to get people on board. The more successful clusters, the ones that are in existence at the moment, have been going for years, because they've understood that this is an element of their emissions abatement programs as long ago as 2006. The first CCS infrastructure I ever sort of put pen to map on looks remarkably similar to HyNet. The plans for Teesside haven't really changed much from Teesside Collective days, but the driver has always been there with the leadership, and understanding the delivery structures and the business case structures, and the commercial aspects is part of that leadership. An individual emitter or an individual storage owner don't necessarily have the skill sets or knowledge to drive those forwards, but those are: how do you structure this for delivery, how do you pay for it, and how do you manage the risk and the assurances that are all in place. The business cases and the delivery structures is a key skill that most major oil majors would have, but actually what local government particularly is very good at. And you have some developing organizations or developer-led organizations that are really good at that, but leadership is the key. Land use, population density, the fact that we've encroached on industrial areas and our industry and our clusters are in historic industry locations is an issue. Where you can and can't put pipelines is becoming more and more complex with the advent of tighter environmental restrictions. We're becoming more clear on where the potential stores are, which makes it easier to target. But if you look at particular problems around some of the design of new infrastructure, and we can show it later on. There's a map, more detailed map than the green one you can see here. You'll see where population density has moved towards the industrial centres, or has evolved from the industrial centres, when having houses right up next door to a chemical plant was a good idea or wasn't thought about. You've got to get your pipeline in. You've got to be able to transport things safely. So we have those to deal with. And that's the encroached industrial areas. It becomes complex. So as part of that, all of those things need to be looked at and considered before you even get to the large technical issues around networks and infrastructure. Emitters are also likely to come online as groups. You will see clusters coming forward. You will see an anchor project in one cluster will start, and then you'll see others go on quite quickly afterwards, because they'll see the benefit and the opportunity. Part of that is an economic driver for each individual company. They've got different things they want to try and achieve, different drivers, but they'll come on as groups. There is a competition for storage. There will be inevitably a competition for storage. Many years ago, in talking to CCS projects, prior to the second phase of competitions, we talked to at least 3 different projects that had said, yes, our store is going to be this, and they named where the store was going to be. It was a nearly depleted hydrocarbon field, but only the 4th project had actually engaged with the owner and said, could we do that? So we'll see competition for storage over time increasing, potentially, depending on how storage offshore is commercially set up. And then there's the other thing of skills and expertise. To design any new infrastructure, you need that skills base, you need the expertise. We've been building a lot of gas infrastructure and electrical infrastructure in recent years, but we haven't really looked at complex new infrastructure for several decades. outside of the small infrastructures that we put in around chemical plants. So there's a skills and expertise gap that needs to be managed and grown, and hopefully after 15 or so years, the situation has got better. But there's an awful lot of people right now that are leaving leaving the business because of age, and those skills and experience will drop off. So something else that we need to be wary of in looking at designing new infrastructure before we even get into the deep technical issues. Can we reuse it? There is a lot of infrastructure in the UK that could be potentially reused, whether it's National Grid's gas networks, whether it's all the oil and gas pipelines that are offshore. Each one needs an individual assessment. So yes, you can use it in theory, until you've done the design work, though, that looks at materials of construction, the method of construction, design conditions, routing, and its suitability to new gases and new fluids. You have to redo all the safety environmental cases. All the mitigation measures might have to be redone. You have to look at age issues and corrosion and inspection, whether an offshore pipeline's been struck or not, all come into play. And you have to look at the system pressure. Not all pipelines are equal. Some offshore pipelines are high pressure, and that's good for carbon dioxide. But the National Grid ones onshore, not so much, because their design pressure is between 70 and 90 bar. And at ambient conditions, that's right in the area of phase transference, where it can transfer from liquid to gas or backward, or the other way around if it becomes static. So you have to look at the system pressure. And some of the infrastructure we've seen would have to be derated effectively. It has been considered in projects. So I know Acorn are currently talking about the NTS feeder 10, but it was originally proposed in Longanet for reuse, and that's a 90 bar, 300 kilometre long line that runs roughly from Grangemouth to St Fergus. And the idea of the Longanet job was to connect that piece of infrastructure. It's 36 inches in diameter. It's an incredibly useful pipeline, but it's got a pressure limit on it. You can't do more than 30 bar through that pipeline. Otherwise, if the line were to be full and go static and it went cold, you'd transfer into liquid, and that gives you a problem in restarting the pipeline. So you've also seen offshore pipelines on Goldeneye and the Shell Peterhead project, and previously on BP's DF1 with the Miller pipeline, all looking at these pipelines saying, actually, can we reuse those for the offshore projects? It would all have worked. So yes, you can use the infrastructure, but you have to go through the process of checking it all. And also, it's always worth saying, if you change the fluid in a pipeline, your planning permission for the pipeline doesn't necessarily apply. So you have to go and do it again. And you might have to renegotiate your way leaves, and you might have to do all sorts of things on the planning stuff and the softer side of project development, rather than the technical, that actually has to happen as well before you get there. Developing the infrastructure. How will projects come to market? So it's a difficult one, but it depends. What are the market drivers? What is driving individual emitters to join a network or to consider CCS? Is there enough emitters in an area to have a common pipeline system? Does it make sense? Is there a store nearby? These kind of things. What support structures are there? Is there funding available, or different commercial models? How do you reduce the cost? And then we've said before, networks reduce the cost. What right sizing? Now, I'm a bit of a fundamentalist on this one. We don't oversize pipes. It gets talked about all the time with clusters that we oversize pipes to accommodate future volume. We don't oversize anything. We put the right size in for the right scenario. Oversize makes it feel like we're wasting money by putting a much bigger pipe in that's needed, but it's actually about taking a step back and understanding the timelines that are involved in the scenarios, and putting the right size of pipe in that will enable the rest of the network to follow. Does shipping enable clusters? I think 10 years ago, if you'd asked that question, everyone would have gone, no, not in the North Sea, but we're seeing it now with Northern Lights and the scenario that they've generated in that they have a pipeline and a shipping infrastructure, and it's going to work fine. It's the ships bring the carbon dioxide from the remote sites into a sea landing where they offload the carbon dioxide onto shore-based storage that then enters a pipeline to stop you having the ship infrastructure offshore for floating unloading. There's that hybrid model will work, and it will be needed for, if you look at any any cluster of CCS emitters or infrastructure that's needed on the south coast, or Wales particularly will have to look at shipping rather than bulk CO2 across the UK. Both options are viable, but the shipping has actually become more proven than it previously was. And there's drivers. What are the economics? What's the energy security issue? What's the technology rollout rate? The policy that we're facing in the UK? We've got the net zero policy that's driving us. Social engagement and the push by consumers to do more comes down the supply chain, as we've seen in the CCS industry, which in the chemicals industry, which actually makes them more involved in clusters. And actually, it also reduces your CCS costs overall if you've got a pool of people sharing the identification and qualification of any storage. So these key factors, I mentioned most. You've got scenario planning, operating parameters, routing, some of the health safety issues, which I won't cover here because they feel like they're forever changing. Dynamics, which we've spoken about, comparisons to source and sink, which we'll get to, which is about cost, and what we can reuse, we've already talked about. But those are the key factors on clusters and infrastructure developing. And we're just going to step through some of those key things. So pipeline networks, just to remind everybody what we're talking about. We have three, illustrated here, we have three storage options: depleted hydrocarbon fields, aquifers. It says single well, but it can be multiple well. It's just it's a bit of an old graphic. And enhanced oil recovery. You've got a trunk line, and we're assuming here that you've got one trunk route, that a common pipeline that feeds into a distributed storage solution, and then you've got the emitters on the front end, which could be from 4 or 5, 2 or 3 different geographic locations, as well as the number of emitters that are there. So you've got that range of emitters. Storage conditions may vary on the storage side, so you have to be very tight on the entry requirements. The emitters will all be different. They'll have turndowns, and there'll be deployment timescales to consider. And those all need to be managed within the pipeline design and the network design and the infrastructure design and rollout, and how you fund that infrastructure. So some very basic design elements actually inform some of the more complicated financial decisions and discussions that have to occur. Now, the next slide has a number of images. Hopefully it will work. That, up until start of last year, is all of the emitters that are listed on EU ETS in the UK, all of them. If you are going to do CCS infrastructure, are you going to pick up all of those? No, you are not. Some will change. The offshore ones will disappear over time anyway, or they'll electrify. But could you put carbon capture onto some of these small emitters offshore? Yes, you could, if that's the way you wanted to go. That's all of them. And these are split into tiers. These very, very small emitters that this first group is, you can see the predominance, the yellow. These are emitters under 50,000 tons. So these are things like hospitals with power plants, or small cogens and large boilers in industrial facilities, those kind of things. The small end that will be the hardest to get at without fuel switching or decarbonisation through electricity or potentially CCS. That's all of the small ones gone, with the next level of emitters. And you can see as you cycle through, these come in phases. If you go to this last one, that's Drax when it was 20 million tons. Go back a sec. And those are major power stations and refineries. And again, you have another group of refineries. So I think the threshold for this one is over 5 million tons, and that one is over 2 million tons, I think. No, over 1 million per annum. So these are your larger members of your clusters potentially going forward. I think anything like that level, which is over 100,000 tons, is roughly where you're going to sit in terms of those that are most impacted by CCS. But what is a cluster? We talk about it, but no one can define it. There is no there's no metric. So I've often described them as three things. There's a social cluster. So is it a business-driven opportunity, or is it an economic opportunity? I say economic opportunity in that some of the arguments around CCS and what binds some groups and organizations together to look at CCS and act as a cluster with a common idea and a common concept of carbon capture and storage is actually driven by the economic reality that if they don't, they're not going to be there. So the chemical plants would close, the power stations might not be there if they don't abate their carbon dioxide. So it becomes an economic opportunity. There's a business opportunity associated with that because you could actually put in a CCS infrastructure and attract people into that area that know, if I go there, at least I've got that option. You've got the emitter clusters. So those are the ones that are driven by the emitters saying, actually, my asset here is going to be here for a good number of years. I need to do something. But they also overlap with the social cluster types as well. So you see on Teesside and Humber in Scotland, and most of the clusters these days are actually very heavily emitter-led, although some over the years have been much more policy-led and the more social-led. And then you have the storage clusters. We don't necessarily have them here, but it's something that will come if someone has a developed store, an identified storage site, or an EOR demand. Then they become they're sticking there. They become the cluster. They become the driving force behind that cluster, and lead the development of it because they have a business case. But there is no defining in technical terms what a cluster is. Concentration of carbon dioxide per kilometer, number of emitters, the availability within a certain area. Is the storage capacity the number of wells, the amount of tons you can put in per square kilometer, and is there a regional political interest, industrial interest? All of those things could be applied as a metric, really. And it doesn't matter. It matters greatly that they're all interested in CCUS. It is not the only thing now. What we're seeing now in clusters is the discussion around what does the cluster enable? Does it enable that economic opportunity and the increased gross value add to the economy of a region? But what else does it enable? And we're having conversations now more about hydrogen and how that fits in to cluster planning as well. And a quick plot of history. This was the Mosey one I was talking about. So you can see a number of storage studies and clusters have developed over time. Cluster influences. It's about defining the baseline, who and where. Where's the storage? Who's the emitter? Where's the emitter location, the timelines, costs, right sizing, optimizing the networks. What are the risks to that timeline? If you design a cluster around an anchor project that's not there yet, what are the risks of that project, that cluster developing if that project doesn't materialize? We've seen that too many times. Too many clusters have reached a certain point that they're ready to go and the main anchor project has fallen. You have to look at deployment rates to understand how it may develop and run, and the expansion, understand the expansion requirements come from those deployment rates, and the influence of mutually supporting infrastructure. We raised that because I've talked about hydrogen, but also how is your cluster going to be impacted by electricity infrastructure, water infrastructure, these other issues, transport infrastructure. There's a lot of different influences in the clusters and how they form and how they can roll out. Who do you include? Always go for the list of who exists and who potentially might come, and anyone who wants to be involved. Governments, financial services, NGOs. Some of the more successful work I've had in understanding the risks and financial issues around clusters have actually been because there's been a bank right there with us telling us what we need to tell them to understand how much money that we need and the assurances they need for that kind of financing. And you filter them. There are some plants that simply you can't include in a cluster for various reasons. You can't get pipeline or transport solution there. It doesn't make economic sense. Those also spill out, and that's where the overlapping infrastructure comes in and the mutually supportive infrastructure, because those sites need to be decarbonised as well. So do you go hydrogen, electricity, or something else? And that helps identify your core design, who needs to be in there, and invariably 5 or 6 people that come up and say we want to design a cluster. This helps them identify the next 10 or 15 that might also want to be, and they have. You might find that the driver from those others actually is the key, the linchpin to developing your cluster and getting support for it. So why cluster? There's no national plan, really. There never has been. It's a desire to do stuff. It allows for diverse ideas, common voices that come from those discussions around the issues that affect individual emitters. It's a multi-sectored approach, and it develops or dispels business models. Some business models have been tested and don't work. It de-risks projects. You have decarbonisation as presents other options, and there's practical reasons like the costs, etc. And I'm going really fast because I know I'm running out of time. Practical reasons to cluster. This is where the nub is on the costs. If you develop transport and storage solutions for multiple users and you right-size the infrastructure, you save money. It saves time on planning. It allows you to optimize that infrastructure design on land use and lowers costs, and the economics. Does it attract new emitters, as I was talking about earlier? And what else does it enable with the mutually supportive infrastructure? And these 2 diagrams show the top one's an example of if you have an emitter that goes to 3 different stores. In the basic way, it's actually, if you plan it right and look at it properly for a cluster, you can see that if you on the diagram below, there's 2 different options of what common infrastructure might mean, and you can see the length of the line shortened, which means your pipelines are shortened, so you spend less money. And on the right sizing issue, if you look at this example, is from a few years ago, when a 12-inch line for a kilometre cost you about £1 million, but if you actually did a 24-inch line, it costs you £1.5 million, but you get so much more through. And you can see that the 12-inch line will easily handle 2.2 million tons, but the one that's twice the diameter, that for 50% more cost will take 6 times more carbon dioxide. And that's where some of the savings with clusters comes in if you right size and do it that way. Routes, it's common sense. Understand where you need to go and where you're coming from. And in looking at clusters and infrastructure design is absolutely critical. And there's a phased implementation and stuff. And this is very quickly T-side. The blue line, it's a very busy diagram, I know, but the blue network line in the middle, you can follow it from left to right down the center of the page, and then it kinks up to the right hand. This shows you what the T-side collective infrastructure looked like in 2015, and this is what networks look like. That network picks up about 20 or 30 different emitters in T-side that individually, if they were A to B solutions, would all be looking at 30 pipes that you have to fit in. By making it common, you have access, you have the ability to thread your way through an area and pick up and make it all so much cheaper for every individual emitter on that network. And this comes down to the cost example. This is from a public report, 2010, it's quite old, but you can see if you look on the left-hand panel, it's easier to read. Halfway down, you have options 11A to D, which are the A to B solutions for some relatively large emitters that were originally on T side. But you can see all of the others are network costs. But if you have the individual sources, even for some of the bigger ones, like the 850 megawatt that IG gasifier that was planned, you can see the network costs across the board are so much cheaper in terms of cost per ton compared to single A to B solutions. And if you look at a smaller emitter, which is a 49 megawatt biomass, even though it's right in the middle of the network, as an A to B solution, you can see that it's about 100 and 120 times the minimum cost of the infrastructure. So there's a significant impact that's driven by clusters in reducing the costs to everybody. And commercial models, I am still not an expert on commercial models. There is a government document that's published which explains it really well and what they're proposing. The link is at the bottom of the page, but it comes down to how do we pay for it, because there is no US-like EOR model. We effectively, do we pay for it to be taken away? But there is a move to an economic regulatory regime, which is explained in the document, and it fixes a cost mechanism for a controlled period, and it addresses ownership, liability, and risk, and finally gives us a structure for infrastructure and commercials to understand how that it work, how can it work, and how could it be costed, and hopefully get to a place where it's understood by everyone and investable. Key issues to resolve, and this is just me, the entry specification impact of mixed streams is critically important. Earlier this week at another UKCCSRC meeting, one of the clients, one of the CCSA technical working groups was explaining that for them, the impact of mixed streams is critical, and how these things operate is not being looked at. Dynamic flow simulation through networks is not done very much, simply because we've never got to the point where someone is seriously designing a network. None of them have gone to feed yet, which is the next level of engineering design. So you've got the operability, the flexibility, how you deal with excursions. What happens when an emitter shuts or when the well shuts? The complexity of operations, the storage impacts and shipping we've all talked about, and the right sizing. But the critical thing with anything is do not sterilize future expansion. You have to find a balance. There will be times when you go, actually, I can't build that big to accommodate an idea, but don't sterilize future expansion. Always leave that option for the network to get bigger if necessary. And this is the entry specification problem. Who and what defines the entry specification for a network? So if you look in this example in storage 4 in blue, it requires 1 ppm part per million volume of oxygen. All of the others are more relaxed and say we'll take 1% mole. That store therefore defines the entire entry specification for the network, and that impacts on all of the emitters, no matter what the other 3 stores say. If you're using a common infrastructure, then storage 4 dictates what you're doing. That's a capex impact on the emitter, and some processes would find it hard to accommodate that because the costs to CCS already may be pushing their economics too hard, and that limits the fluid. Or could a emitter 3, for example, offset a dirtier fluid because emitter 4 has a clean fluid? Just some issues to consider. And again, something that was covered in a UKCCSRC meeting earlier this week. But those are the kind of things that need to be looked at. Those are the next challenges for clusters, is to do the modeling. But what else does it enable us to do? And I'm nearly done. It enables us to, and allows us to look at decarbonised energy. And that's not just about the hydrogen story. That's also, could you, BECCS falls into that, biofuels, decarbonize industry where electrification might not be an option via hydrogen or something else, or synthetic fuels made from the carbon dioxide that we're capturing. What else does it do? There's still some options and things to look at, and it's nice to see the current clusters most of whom are considering hydrogen as part of that story. There's other challenges as well. Does it look at road fuels? Does it allow industrial heating to adapt? Does it allow buildings, the domestic sector, heating power via hydrogen or something to decarbonise to a certain extent? We go back to 2006 when the first question I had about CO2 infrastructure was, how do you get it out? How do you capture all the CO2 at your house to then take it to a common capture plant? We didn't know where to start, I think. And it enables the blue hydrogen argument. And that's what this diagram is. And it's here simply because this is what occupies my mind at the moment, in that you have the carbon capture and storage infrastructure on one side of the blue hydrogen infrastructure, and you have the blue hydrogen infrastructure and how the interplay between these two, knowing that CCS infrastructure is not very dynamically modeled at the moment, and we're not really looking at it in the detail I think we should, but we are for hydrogen now looking at how we do that, and it is a very high, highly variable flow that hydrogen has to adapt to? Yes, but finding the balancing point so that the infrastructures support each other rather than cause each other problems. And that is me done. I'll get rid of that one because it's the wrong one. So thanks for listening. I hope that's been interesting, and I'm probably very over time. So I think it's over to questions, Karis.
Yeah, we're pretty relaxed, James. We'd like to get good people off. Can I just ask a question? We've had a few things come in. What about line packing with CO2 and actually line packing with hydrogen as well?
I'll take the last one first. Hydrogen is something we're looking at, and it's easier to do because it's a gas. And we would expect it to form a normal part of operation of hydrogen networks, would be line packing. For CO2, if it's gaseous CO2 in a pipeline, then you can have some, but the opportunity is not there if you're operating in dense phase or liquid, just because the density difference is not that great. You can do it in CO2 pipelines because you can potentially run if the pipeline goes static, or you can run it at higher pressures without tripping it over into liquid, then you can gain some. I think the numbers off the top of my head, when we looked at Longannet, which is a 300-mile long gas pipeline, line packing in that system only bought us 8 hours of response time. And that's what we were looking at it for, is if something went wrong, how long could we line pack for before we had a problem? And it was only 8 hours worth. And that was simply to do with the pressure limit on the pipeline at 30 bar.
And that was 1 million tons a year scale, so it was relatively small.
Yeah, but it was 1 million tons a year because that's what Longannet was putting out. The pipeline could take up to about 6 or 7.
But it wouldn't give you 8 hours line packing then?
No, it drops off the...
An hour.
Yeah.
Yeah, interesting. Okay, and somebody raised a question about, just when you said about large units in clusters, what the deal was with those. Were you just saying that you're a bit vulnerable if they close down?
You are, and and there's evidence for it. If you look historically over where we've got to in terms of cluster developments, and I use Teesside as an example simply because I live on Teesside and I know the project quite well. The original large emitter that was driving CCS cluster discussions in Teesside was the Eston Grange power project. When it didn't qualify for competition 1, the project stopped, and there was I guess it was a lack of emphasis in the area and a driving. It lost its leadership because it didn't have the proactive nature of the power station there to say, yes, we're going to do this, we're going to do that. The time it came round to competition 2, which would have been around 2013, we had Teesside Low Carbon, which was the same project as Eston Grange effectively, but slightly modernised.
What sort of power plant was it?
Gasification, IGCC. It didn't qualify in competition 1 because it was an IGCC, and didn't qualify in competition 2 because it was beaten by White Rose and Peterhead. But at that time, when they were coming with Teesside Low Carbon, you had Pixie, which was the name of the group on Teesside that was the local supporters of CCS. And when that project got cancelled, there was a bit of a period when there was not a lot of CCS discussion on Teesside until the Teesside Collective in 2014, when the local politician, the local LEP, which is now Tees Valley Combined Authority, effectively said, look, this is an economic argument for keeping the chemicals industry in this area and keeping our economy sound, that we have to address CCS. And we saw then, with the drop of both the big anchor projects, you lose the emphasis unless you're in that social cluster envelope where there's a political or policy driver that drives you forward and keeps everyone motivated. That's what I meant by that. We've seen it before on other projects as well, that if the anchor project packs up and doesn't qualify or can't find funding, then it can stall CCS developments and development of clusters.
I had a question about to explain blue hydrogen in the context of CCS.
Okay, so
it's not really blue, is it, James?
No, it's not really blue. That harks back to a conversation years ago when someone from the government said, how do you put hydrogen through a gas burner on a cooker, and how do you put color into it to make sure everyone can see the flame? And we said add methane. He didn't appreciate the joke, but there's this thing in hydrogen that everyone seems to like labels, and there's a rainbow of hydrogen. And it depends on the source of the hydrogen. So green hydrogen is hydrogen via electrolysis from renewables. Turquoise is looking at advanced methanation and pyrolysis of methane to get carbon black. So you sidestep the CO2 issue.
And what do you do with the carbon black?
Sorry?
What do you do with the carbon black?
That's the question I had for them as well, because there's only so much carbon black you need, but they were started talking about biochar and ground remediation, etc., and I was just like, yeah, okay, thank you, I'll move on. The blue hydrogen concept is that if you most commercial hydrogen in the world is generated via the reformation of or the reforming, I should say, of hydrocarbons, so mostly gas, and that's how it's accomplished in the UK at the moment. Certainly at the sites we've got, and that emits carbon dioxide. So it splits the methane molecule, and steam methane reformers add water, so you get more hydrogen and more carbon dioxide. So that carbon dioxide has to be abated and captured. Now, in some cases, on where this process occurs, like on ammonia plants, a lot of that carbon dioxide is captured already and used in the food industry. So what we're looking at for the hydrogen economy is blue hydrogen is exactly that. It is hydrogen generated through the traditional means, or the next generation of those means with ATRs, from hydrocarbons, but the carbon dioxide emitted from those facilities is abated and uses CCS to dispose of the carbon dioxide. So technically the hydrogen has a very low carbon footprint because of the CCS infrastructure and the ability to store the carbon dioxide.
Okay, thanks. I'm just going to ask the questions just because we're a little bit short of time. So how useful do you think EOR will be? Transport of CO2 for EOR will be compared to?
As useful for storage. I think it adds a different economic driver, and if it was the prevalent discussion point in the North Sea.
How useful will the experience be, the learning?
Oh, significant. There's no getting away from that. The pipeline knowledge that we have is coming from that EOR market. There's plenty to learn from how they've done it in the management of these systems, but a lot of the systems in the States aren't networked systems. There's not that many that come from multiple emitters to multiple sources to multiple wellheads. There's plenty that come from one or two, or geological formations that go to multiple wellheads. So on the wellhead management side and the distribution of CO2, then there's a lot to learn, I think. But we will try and take as much knowledge from every sector as we possibly can.
Yeah. And then a question, how far away do you think we are from transnational CCS clusters, and what do you think they might be? What do you think might be the focus of a transnational cluster?
It comes back to how you define clusters. I think you'll see, if you're looking at transnational, then you're looking more at storage driven, in that you have a store that attracts people from different nations. They have to get past the border regulations and the policies that each individual jurisdiction has. I can see it happening in the North Sea and in other places, but not anytime soon. I think the closest to it is actually if you enabled, if you had a remote region that chose shipping and they came to an agreement with Northern Lights, then that would be eminently doable. But yeah, it's
certainly looking at that for Northern Lights pretty close, really, I think.
Yeah, I'd put it all in. I'd put transnational in the too hard box. I'd rather just build. I'd rather build one right now and then understand that transnational will probably come in from national infrastructure operating remotely, and will, I can certainly see in the future, if we continue with carbon emissions even in a much smaller shape and form, and if we go with some of the hydrogen plans, then I can see the European Union and the UK having to cooperate about stores in the North Sea.
I suppose there's the Weyburn pipeline, which goes from US to Canada.
Yes, yeah. But again, it's driven by EOR because it's a commodity, it doesn't count as a waste, so the waste regulations don't apply. Whereas here it does.
Yeah. Pretty good. Okay, well, unless there's any more questions, I think we probably better stop because people have got to get on for the next meeting. So, James, thank you. That was really excellent. Really good. Yeah, we might try and get you back more than once a year.
I'm quite, as you know, John, I'm quite happy to come and talk until the cows come home.
That's
and given half the chance, I will. I
think what we'll do if we do that, which is always the best bit, we'll really try and get some discussion going, because I'm sure when we get perhaps even when we can have some physical meetings again, we can have a different dynamic too.
Yeah, and in the meantime, my email's right there on the page that people can see. If anyone's got any questions they want to follow up, just send me an email. I don't know if I'm a rare beast, but I want to see this stuff built, and I don't mind answering questions if it enables other people to start to contribute in some way. So yeah, if anyone's got any other questions, just drop me an email.
Yeah, well, and you're certainly getting a lot of appreciative comments on that, so that's really great. Okay, we better pass on to Karis. Any final comments?
No, not really. Just to say, a big thank you to James, and that was our last lecture of the spring series. So I think we've finished on a couple of really good lectures as well, and it's been a great series. So we're going to be taking a couple of weeks break just over the Easter from the web series, and we'll be starting again on the 15th of April with the summer web series, and that will start with an update from Bryony Livesey from UKRI. So looking forward to welcoming Bryony in a couple of weeks' time. In the meantime, we hope you all have a nice for the Easter, and some of you, everyone manages to find a bit of time to rest over the Easter period as well. So thank you everyone for attending today, and a big thank you to James. And yeah, have a nice rest of the week.
Thank you.
Thank you.